You must have seen your mother drop naphthalene balls in boxes containing woolens. And I'm sure you know that naphthalene balls are used because they repel moths due to their unique smell. But do you know what naphthalene balls are? Keep thinking. Welcome to an aromatic episode of chemistry. I am Deobrata Goswami, and today we will find out more about compounds which have a pleasing smell. These aromatic hydrocarbons are also known as arenes. Before we begin, let's take a look at what is in store for us today. Today we will learn what aromatic hydrocarbons are. We will also figure out what aromaticity is. And we will understand the IUPAC nomenclature and structure of benzene. Finally, to gear you for the exams, we will look at the important questions in exam decoded. So what are aromatic hydrocarbons? Aromatic hydrocarbons have a molecular structure that incorporates one or more planar sets of 6 carbon atoms. These are connected by delocalized electrons and consist of alternating single and double bonds. Aromatic hydrocarbons are of two types, benzenoid and non-benzenoid compounds. Aromatic hydrocarbons containing benzene ring are called benzenoids, and naturally those which do not contain benzene rings are called non-benzenoids. Benzene, naphthalene and anthracene are some examples of benzenoid compounds. Like I just said, naphthalene belongs to the benzenoid class of aromatic compounds and is derived from coal tar. Mothballs, as we discussed, are made from naphthalene, as naphthalene easily sublimates or exudes gas. That is why it is also sometimes used as a fumigant. Coming to anthracene. Anthracene is an organic semiconductor. It is used as a scintillator for detectors of high energy photons, electrons and alpha particles. Now let's take a look at examples of non-benzenoid compounds. One of them is tropolone. How do we know which compound is aromatic? For a compound to be aromatic, the first condition is that the compound should be planar so that the pi electrons are delocalized in the ring. The second important criterion is that it should have a complete delocalization of pi electrons in the ring. And finally, it should obey the Huckle rule. The Huckle rule states that the compound should have 4n plus 2 pi electrons, where n is an integer with a value starting from 0. Let us now put benzene to this test. In benzene, all the carbons are sp2 hybridized and hence it is a planar structure. So, it satisfies the first condition. Benzene also has alternate single and double bonds and hence complete delocalization of pi electrons is possible. So, it satisfies the second condition as well. Now for the third condition. Since benzene has 3 pi bonds, it has 6 pi electrons. Thus, it satisfies Huckle rule. Have you ever wondered what makes aftershaves so aromatic? Yes, it is the compounds of benzene that make it so. But now, let's see how we name these aromatic compounds. Here are the rules. Since we know that benzene contains 6 equivalent carbon atoms, therefore, it can form only one type of monosubstituted product. In order to name monosubstituted benzene compounds, we take the benzene ring as the nucleus and the groups attached to the ring are the substituents. The name of the substituent is added as a prefix or suffix to benzene. For example, if a chlorine group is attached to the benzene ring, the name of the compound becomes chlorobenzene. And if a COOH group is attached to the benzene ring, the name of the compound becomes benzoic acid. Now, let us study the nomenclature of di-substituted benzene. In a di-substituted benzene, two hydrogen atoms are replaced by two similar or different atoms or groups. As a result, three isomeric structures are possible. In benzene, the carbon atoms are numbered from 1 to 6 as shown. When the substituents are present at the first and second or the first and sixth positions, the isomer is called orthoisomer and is denoted by the letter O. Such compounds are named by indicating the position and the name of the substituents as a prefix before benzene. For example, if two Br groups are present at 1 and 2 positions of the benzene ring, the name of the compound becomes 1,2-dibromobenzene. It is also known as ortho-dibromobenzene. If the substituents are present at the first and the third or the first and fifth positions, the isomer is called meta-isomer and is denoted by the letter M. Let us take an example of these compounds. If two Br groups are present at 1 and 3 position, the name of the compound becomes 1,3-dibromobenzene. It is also known as meta-dibromobenzene. Next, if the substituents are present at the first and fourth positions, the isomer is called para-isomer and is denoted by the letter P. An example of a compound of benzene forming a para-isomer is 1,4-dibromobenzene or p-dibromobenzene. Well, that was a lot of information, and I think you need time to digest it. So, we will take a short break here, but don't go anywhere. There is a lot more coming up after the break. Here is a question to keep your mind ticking. Can you name the first scientist who isolated benzene? And there is a story attached to this discovery as well. But I will tell you that when I return from the break. Keep thinking. Welcome back. I am Deobrato and you are watching Chemistry 11. Before the break, I had asked you who was the first scientist to isolate benzene. Well, benzene was isolated by Michael Faraday in 1825. But as I said, there is a story associated with it. Benzene was isolated in 1825, but it took 40 years for another scientist, Frederick Kekulé, to come up with its structure. How did he do it? Well, scientists follow a simple method. They collect data by experimentation, analyze it, and then form theories on that basis. Then they do more experiments to test that theory. That is exactly what Kekulé did for benzene. A number of reactions were carried out and their products were analyzed, and interpretations were made on that basis to assign a tentative structure to benzene. The molecular formula of benzene is C6H6. Since this did not match with the alkanes, alkenes or alkynes, benzene was believed to be a highly unsaturated compound. The presence of 3 double bonds in benzene came to the fore when it formed a triozonide on reacting with ozone. It was observed that benzene gave only one type of monosubstituted products. This indicated that it is a symmetrical molecule with all carbons and hydrogens being equivalent. Further, this gave rise to the possibility of benzene having a cyclic structure. The fact that benzene has a cyclic structure and 3 carbon-carbon double bonds was confirmed when 3 molecules of hydrogen were added in the presence of a nickel catalyst. The product of this reaction was cyclohexane. But finally, it was a moment of inspiration that led Kekulé to the structure of the benzene ring. Kekulé wrote later about it. Apparently, he dreamt of a long snake-like structures. One of the snakes took its tail into its mouth. It did not take the scientist long to figure that one out, and he woke up to a new hypothesis. Auguste Kekulé proposed that benzene is a cyclic planar molecule composed of 6 carbon atoms with alternate single and double bonds and 1 hydrogen atom attached to each carbon. According to this, benzene was simply 1,3,5-cyclohexatriene. Though this finding was quite a breakthrough, there were a few objections to this structure. According to this structure, 2 isomers of ortho-dibromobenzene would exist. In one of the isomers, 2 bromine atoms are attached to the singly bonded carbons, whereas in the other isomer, they are attached to the doubly bonded carbons. However, benzene was found to form only 1 ortho-dibromobenzene. What was the reason? Kekulé had an answer to this. He proposed the concept of oscillating nature of double bonds in benzene. Thus, there are 2 structures possible for benzene. The story is still not complete. If benzene oscillated between 2 structures, then with 3 double bonds, it would undergo addition reactions like other alkenes. However, it was found that benzene had preference for substitution reactions. So, there was a need to look at the structure of benzene from a new perspective in order to justify all the observations made. The new perspective came through the X-ray diffraction studies, which showed that the internuclear distance between all carbon atoms in the benzene ring is the same. The length of all carbon-carbon bonds in benzene is 139 picometers. It clearly lies between the carbon-carbon single bond and carbon-carbon double bond, which are 154 and 133 picometers respectively. This shows that there are no pure single and double bonds in benzene. In other words, benzene does not exist in either of the 2 structures given by Kekulé. It is a resonance hybrid of both the structures. In fact, the concept of resonance came into being because of benzene. That was interesting, right? If you analyze any scientific discovery, you will find that it usually began with a question, just like the question that has arisen in the mind of our young caller today.
What does the dotted circle in the benzene ring represent?
Thank you for the question. Well, the dotted circle in the benzene ring represents the resonance structure of benzene. This can also be represented by a normal undotted circle. Basically, the circle represents the 6 pi electrons which are delocalized between 6 carbon atoms in benzene. Let us take a look at the orbital diagram of benzene to understand the structure of benzene better. As you can see here, all 6 carbon atoms are sp2 hybridized. So, for each carbon atom, we have 3 sp2 hybrid orbitals and 1 unhybridized p orbital. 2 sp2 hybrid orbitals of each carbon atom overlap with sp2 hybrid orbitals of adjacent carbon atoms to form 6 carbon-carbon sigma bonds. The remaining 1 sp2 hybrid orbital of each carbon atom overlaps with s orbital of a hydrogen atom to form 6 carbon-hydrogen sigma bonds. Each carbon atom is now left with 1 unhybridized p orbital which undergoes sideways overlapping to form 3 pi bonds. There are 2 possibilities of forming the 3 pi bonds. One is by the overlap of p orbitals of C1, C2, C3, C4, C5, C6. And the other possibility is by the overlap of p orbitals of C2, C3, C4, C5, C6, C1. That was all about aromatic compounds. But do you know there are a special class of aromatic compounds known as polycyclic aromatic hydrocarbons or PAH. These are chemical compounds that consist of a number of fused aromatic rings. PAH occur in oil, coal, and tar deposits and are produced as byproducts of fuel burning. PAH are also found in cooked foods such as grilled meats. And for the space enthusiasts, PAH are also found in the interstellar medium, in comets and in meteorites. In the environment, PAH are found primarily in soil, sediment, and oily substances. Polycyclic aromatic hydrocarbons can be formed from any naturally occurring fire, such as bush or forest fires. They are emitted from active volcanoes. These compounds are hazardous to aquatic life and birds as they are fairly toxic. Some cause damage and death to agricultural and ornamental crops. It's time for another break now. But don't go away because I'll be back with Exam Decoded in just a bit. Welcome back everyone. I am Deobrata Goswami and we are studying aromatic hydrocarbons today. Let's take a quick look at all that we have learned so far. Today we learned that aromatic compounds are of 2 types, benzenoid and non-benzenoid. We also learned the conditions for a compound to be aromatic. For a compound to be aromatic, it should be planar, its pi electrons should be completely delocalized, and it should obey the Huckle rule. And according to Huckle rule, an aromatic compound should have 4n plus 2 pi electrons, where n is an integer. In benzene, each of the 6 carbon atoms are sp2 hybridized. Well, it's time for the segment you have been waiting for, where we decode and demystify exams for you. Welcome to Exam Decoded. It's now time for the rapid fire round. So brace yourself. I will ask you 5 questions. You will get just 5 seconds to answer each one of them. Every right answer gets 1 mark. Ready? Here comes your first question. How many monosubstituted products does benzene form? A, 1, B, 2, C, 3, D, 4. Well, the answer is A. Benzene forms 1 monosubstituted product. The second question coming right your way. Which isomer is formed when the substituents are present at the first and third position in benzene? A. Orthoisomer, B. Meta-isomer, C. Para-isomer, D. Beta-isomer. Well, the answer is B. Meta-isomer. If you didn't get that right, don't worry. Here comes the third one. With which letter is the isomer form denoted when the substituents are present at the first and fourth position? A, O, B, M, C, P, D, S. The answer is P. Now for the fourth question. Naphthalene is a non-benzenoid aromatic compound. True or false? It's false. We are now just left with one question. According to Huckle rule, an aromatic compound should have 4n plus 2 pi electrons in the ring where n is an integer. True or false? Well, the statement is true. I hope you enjoyed the rapid fire round as much as I did. Let's see how you have fared. If you scored 5 on 5, then you are a high flyer and I bow to you. If you scored a 3 or 4 on 5, then you are an achiever and you have the potential to soar high. But if you scored less than 3, then you need to work a bit hard. But don't worry, www.topperlearning.com is just a click away. Let us now discuss what you can expect in the exams from this chapter. This topic, aromatic hydrocarbons, comes under the unit hydrocarbons. It carries a weightage of 8 marks, making it critical from the exam point of view. The questions asked from this topic range from very short answer type questions for 1 mark to short answer type questions for 2 or 3 marks. The questions covered from this topic can pertain to knowledge ability and conceptual ability. So I hope you paid good attention to whatever I taught you today. But knowledge alone may not be enough. Presentation is also very important. So if you want to impress your examiner, here is an ideal answer for a question from this topic. Cycloheptatrienyl cation is aromatic or not? Justify your answer. If this question comes for 3 marks, here is how you must answer it. Cycloheptatrienyl cation is aromatic because it satisfies all the 3 criteria for aromaticity. The criteria are: the given compound is planar since all the carbons are sp2 hybridized. Mentioning planarity will fetch you 1 mark. The given compound has a complete delocalization of pi electrons in the ring. Writing about delocalization will fetch you another mark. Cycloheptatrienyl cation has 6 pi electrons. Thus, n in 4n plus 2 becomes 1, which is an integer. So, it satisfies Huckle rule also. Writing the third condition will give you the remaining 1 mark. Finally, we have come to the end of this episode. Remember, knowledge has no boundaries. Do you know benzene was once used in gasoline to increase its octane rating, but is not used nowadays? This is because benzene has carcinogenic properties. I'll take your leave now. See you next time.